Yeah, so short bit about me. So I've been doing TCP/IP and internet-based stuff since '84. I started doing DNS in large scale in 1990, the landscape has changed pretty dramatically in terms of how it's been abused over the years, both deliberately and inadvertently. I'm going to go through a few basics first, just so that we have all of the terms. We tend to get very sloppy sometimes in where we describe the various roles of our DNS, and I'm going to be doing some case studies with this, and I want to make sure that we're all on the same page and you're understanding the context of how I'm using those, so when we describe it, you're getting exactly what's really going on. So first off, zone owner, that's the person who actually owns the brand name, whatever you want to call it. They are the ones that actually care if that domain name functions correctly. In this parlance, a DNS operator is whoever is running the visible authoritative name servers on the internet, whether it's anycasted or unicasted, but not the hidden masters, not anything else, but the operator of the public authoritative servers. And this is the one that I always used to confuse. Registrars are the people that you buy domain names from, and the registry is the actual database that constructs those TLDs. I can buy a .com domain name from any number of registrars, but VeriSign runs the registry that actually has the stuff that goes into .com to do those delegations. There are also a bunch of roles, and we'll be talking about this because these are all now attack surfaces, and unfortunately the bad actors in many cases are more knowledgeable and more sophisticated than the sysadmin who may have inherited the DNS infrastructure. So it usually starts with the stub resolver, and that's most likely to be part of the operating system of the device that is actually making the DNS query. And in most cases, it is literally a stupid stub, and it just goes to whatever was configured via DHCP or in your resolve.conf or in your registry, and goes and asks a fully recursive resolver for the answers. Some operating systems like Windows and Macs do actually also cache for 5 minutes within the stub resolver, but that's not a requirement. The recursive resolver is the one that does all of the interesting work. It is the one that will go through all of, starting at the root and going through all of the delegations to get to the point where it gets to the name server that has the answer for the original question, and it then sends it back to whoever asked, usually, as I said, the stub resolver. In this case, almost always fully recursive resolvers are also caching, so that they can give the same answer again to other clients without having to go through all that work and give the answer faster. And then the other side of the picture are the authoritative servers, and these are the ones that actually have the zone data for that particular domain name that you're interested in, and answer only for that. This is in the slides. It's mostly there to show that basically the device asks the question, it goes to the caching recursive resolver, and then it will walk through the entire tree. The only thing of interest here is that in the old days, everybody, including the root server, got the full question. If I wanted www.example.com, that recursive resolver actually asked the root server for www.example.com, even though the only thing it's going to get is a referral to who has answers for .com. QNAME minimization is a standard that is starting to roll out fairly widely, and that's the one where you only put as much name into that query as you need to get that answer. So the root server will only see a question for .com. They won't see www.example.com. And the common security problems that we see and that we're hoping to address, one of them is simply denial of service, guaranteeing that you were unable to get an answer for that zone. Probably the most notable example in recent history was the Dyn outage in 2015, where basically they melted connection points such that you couldn't get to their authoritative servers, and little useless things like Twitter disappeared off the face of the earth. One of the other ones which really drove DNSSEC deployment back in 2008, cache poisoning, and we'll talk more about exactly what it means when you poison the recursive resolver's cache. People set up false authoritative servers, so if I can get you to go to something that isn't the server that's supposed to be there, it's not the DNS operators, it's one that I, as the bad guy, am running, I can put whatever zone data in I want. I can change where your web queries go, I can change where your email goes, I can set up man-in-the-middle or honeypots, I can do all sorts of nasty little things if I can convince you to go to this server that is not the real authoritative. And then finally, if you can get the credentials for the zone owner or whoever maintains the zone data, and you can actually go into that zone, I don't even need a false authoritative server. I can just change the data within the DNS zone itself. And so primarily these are what we are seeing in DNS attacks. I'm not going to be talking about some of the other things like DNS tunneling, where DNS is used as another means for command and control. This is about hijacking the DNS data itself. Results of those, obviously, you get no answer at all. So your business is off the internet and failing to take anything. Or I can set up a fake site. And if I can set up a fake site and I can get to your users to go to that instead, I can steal login credentials. I can give out false data. I can give embarrassing alternatives. Or I can quietly make it look like it's working normally, and I can eavesdrop on your email or your web traffic or other things. So, some DNSSEC basics. In the simplest terms, DNSSEC is just public key or asymmetric encryption. And the way that works is you generate a pair of keys, one of which is public and given out widely, and one of which you keep very secure and private. And those pairs of keys allow you to either sign or encrypt data. Private keys are always kept very secure, because if someone can get your private key, they can counterfeit as you, or they can decrypt things that you wanted to keep secure. In the DNS use of this, they do it with digital signatures. Nothing is encrypted with the keys, but there are signatures so you can validate that nothing has changed. And since DNS publishes anyway, and public keys are supposed to be widely available, they've taken advantage of that, so the public keys are actually put into the zone with other zone data, along with the signatures. And you can take those public keys, and you can take those signatures, and you can walk that whole chain through, and you can then use those to validate all of the signatures. And if you can do all of those, you have assurance that whatever DNS answer you got has not been modified from what is in the zone. And if for some reason validation does fail, if you are DNSSEC signing your data, but that answer fails to validate, the user will get no answer. So if somebody does something malicious, the user is protected from going to that bad site because they won't ever get the A record or quad A record. So first we'll talk about what DNSSEC actually solves and what are the problems that we're talking about in security that it potentially could solve. So most people, when they break down security, will describe that there are certain key things that you need to be able to do or not do. Confidentiality. Can I prevent anyone who's not authorized from getting this data? Integrity. How do I know that someone hasn't in some way modified the data from the original sender all the way to me as the recipient? And availability. Can I get to that data when I want that data, or can someone prevent me from getting it? So DNSSEC solves the integrity problem because when I put it into the zone and I digitally create signatures for it and publish the public key and do all of the stuff that I need to do, you can go through and validate, and you can tell that what I put in the zone file actually got all the way there. So cache poisoning, because DNS generically is UDP based, I can send a single packet as a DNS response. And that resolver, if it's asked for the answer to www.example.com and a UDP packet comes back that says the A record for www.example.com is 1.2.3.4, and I'm not doing DNSSEC, I will stick it in my cache. And in 2008, Dan Kaminsky did some research, and talk to me offline if you want the really gory details, but there's something called the birthday attack, which basically says that counterintuitively, if I have 50 people in the room, the chance of 2 people having the same birthday is 80% or whatever it is, but within a fairly finite amount, somewhere in the low 500s, I have a 99.9% chance that there will be collisions. And so what Dan discovered was if you simply sent 400 or 500 packets with responses that were bad or malicious, at the same time that you could generate a query for that answer, the odds were almost guaranteed that the cache would take that instead of the legitimate authoritative server's answer, and they would cache it. And of course, they would also put a TTL that was really, really long, so that that answer stayed in that cache for a very long time. And so what happens is everybody who then asks after that cache is poisoned gets the malicious answer. DNSSEC, because the caching server won't cache it unless it validates, if it fails to validate, it simply throws that answer away. So the most effective thing that we have right now for cache poisoning is DNSSEC because of that integrity check. We know that the answer is what was supposed to be in the zone data, or we don't accept it at all. It also means that if I set up a false authoritative server, I don't have the private key, so I can't sign those records, so none of them will validate. And so again, if I manage to somehow get you to come to a false server, but the correct zone is signed, you won't accept those answers either. So in both cases, what this means is the end-to-end integrity, from the original source of the zone file all the way to the stub resolver and into the device or app that asked, we can know that it's the same and it hasn't been modified in transit. Okay, that's great. But DNSSEC doesn't solve every problem. One of them, it doesn't encrypt. All DNS, even DNSSEC signed, still goes in the clear. So anybody who is in the network path and can observe packets going by can see the query and the response. So if you don't want someone to know that you are going to AIDS.org, like your insurance company, that's a problem, because if somehow they can see that data going by, they know that a particular IP address in a particular home is asking about a particular DNS answer. So confidentiality is definitely one of the things it doesn't do. It doesn't fix availability. I can still disrupt things by breaking signatures, clogging links, knocking you off the net, DOSing your machine, whatever. It also, you get what's in the zone, but that doesn't, it's not autocorrect for DNS. If I fat finger something and put the wrong name or the wrong IP address into my zone file and I sign it, you will get something and it will validate, but that doesn't mean it will work. And finally, you don't, by signing your zone, control the parent. So for example.com, you have to trust that whoever's running .com is doing something to be sane and secure themselves. But you doing DNSSEC doesn't necessarily mean that your parent is secure. And if they're not signing, you can't use DNSSEC because it must be a complete chain all the way from the root all the way down. There are ways of doing things with additional trust anchors and other things, but they are not clean and they still don't mean universal availability of that DNSSEC validation. So I'm going to talk now about the meat of this. Now that we've sort of explained the ground rules and a little bit about what DNSSEC is not, I've got some examples of DNS hijacking broadly. And in the broadest sense, DNSSEC or hijacking is you somehow manage to make sure that the intended consumer of that DNS answer gets the answer you want them to have, not the correct answer. And there are a number of places that, because there are so many attack surfaces, that you can subvert that data. And I've picked some recent ones. There was an incident with a Brazilian bank. There was a website defacement for the WikiLeaks site. There was an Ether wallet, Bitcoin cryptocurrency issue. And then most recently, what they're calling DNS espionage, which is actually nation-state plumbing and exploration of other sovereign nations. So Brazilian bank was fairly straightforward. It was a Brazilian ISP was giving out cheap CPE routers that had unpatched bugs. And as we all know, consumer-grade CPE routers are the gift that keep on giving. And so they figured out a way of changing the resolver from the stub resolver that was in the router to their own code. And in most cases, for most home setups, your CPE is also your home router, and it does the DHCP. So all of the devices in that home will change their recursive resolver to use that router as the resolver. And what they did was they simply had this code work correctly for everything except for a particular bank that they wanted to target. Any queries for that bank instead gave answers for a fake site that they set up. And since they could control what site they went to, they basically had a little man in the middle, and they watched everybody's login and password as it went through, and then they logged you in helpfully to the bank. So customers didn't notice until those credentials were used and they started emptying bank accounts. So the result of this was basically a number of Brazilian banking customers lost the money in their accounts. So remediations for this are pretty straightforward. The biggest thing in this case would be actually running decent, secure, and currently patched routers, because they wouldn't have been able to put the code on. DNSSEC would only have been useful if the individual devices in that home had themselves been doing validation, because they would have then noticed that what the router gave them didn't validate. And at least at the moment, there is code, the Stubby project and a couple of other things, for trying to come up with validating stub resolvers small enough to fit onto devices, but that's certainly not common at the moment. And then regular searches for malicious certs might have given them something, because if they went to the bank and it was HTTPS, they might have noticed that somebody got www.brazilianbank.com with a CA that they didn't use or with a cert they didn't expect. That one, unfortunately, is much harder to catch, and we'll sort of bump into this with several of these. Certificate transparency logs and some of the attempts at that or pinning are trying to make the whole CA mess less of a festering security pile, but it's kind of fundamentally broken at the moment. WikiLeaks was actually much more simple. They basically somehow got the account credentials for the zone owner, and they just went in and changed the IP address on the A record. So it looked like their site had been hacked, and they said, we have hacked the website and blah, blah, blah. But that wasn't true. The website was out there, just no one was going to it because they were going to a false one. And in this case, very simple, credentials, keep them secure. And if they'd had DNSSEC, and if they'd actually checked to see that everything was up in the parent and hadn't changed, it might have given them some more warning. But that's another, and we'll get to this with the last attack that we were covering. DS records and NS records and parents tend to have very long TTLs, so most of us don't check them very often, which means that if you can change things in the parent, life gets really dicey and it's actually very hard to catch. My Ether wallet, a little bit more interesting. What they figured out was they could actually do a BGP route hijack of the actual IP address of the website. And so the real website was still up, DNS was still working, and most people were getting to the correct website. But enough of them wound up getting along the hijacked route and to the fake one, and they didn't do their certificate stuff right, but unfortunately we've also trained users of this certificate doesn't match, is that okay? Click. And they punch right through. And so they did. They went to the fake site, their credentials were stripped, their accounts were emptied, and cryptocurrency went away. So this is one where we're getting sort of into the core of what NANOG preaches anyway. BGP and routing security obviously would have helped this. And if more people were implementing RPKI and doing drops and not just logging, they wouldn't have been able to take care of this. And that would have been the most useful thing. DNSSEC might have helped a bit, but once again, if users are willing to click through certs and other things, it might have made it easier to notice earlier if they had been actually looking at that, because validation would have failed for some of the stuff. But they would have also had to have probing that was sufficiently distributed across enough ASs that they would have had some of their probes actually in the areas where the hijacked route won. That's another one of those why doing things with Anycast is really cool for robustness, but really hard to debug if something goes wrong. And then again, watching your certs is certainly something that everybody should be doing. Unfortunately, it's unclear how practical in real terms it would be at catching this. So now we get into probably the most interesting of them. This was a campaign by the Iranian military. They have a cyber hacking team, and basically they come in every morning and go to work seeing what they can do to find credentials for people that they don't like. And in this case, the two biggest winners or losers were UAE and Lebanon, who they had concerns about. And so at some point in time, they had managed to get, via a data dump they'd gotten from a previous hack and then stripping of data, EPP credentials. So EPP is the protocol that when a registrar makes a change that needs to go into the registry, so I register example.com and they need to insert something into the .com registry, the protocol that they use via API to do that is EPP. And EPP uses certs, which are effectively just like a password or an SSL cert. And so they got the credentials for a couple of registry operators, including NetNode in Sweden and PCH, Packet Clearinghouse. And now these are people, they know DNSSEC, they are very technically sophisticated, but somehow someone had leaked some of the EPP credentials. So they were actually able to get into the parent. Now, fortunately, the Iranians were not terribly DNSSEC savvy, because if they'd been really good, what they would have done was they would have made sure that DNSSEC wouldn't possibly ever be an issue by simply taking the DS records out in COM for example.com. Now you can't possibly sign example.com, nor can you validate it. Fortunately, they did not. What they did do was they changed the NSs. And interestingly enough, what they were doing was they were trying to fly under the radar. So this was happening over December and January when most of the world was on holiday. And that was apparently a very deliberate choice. And they would change the NS for an hour at a time and then change it back. So they also, interestingly enough, they did understand enough to know that Let's Encrypt, which is usually what they use for getting their fake certs when they set up their man-in-the-middle websites, it actually checks for CAA records in the zone, and it actually DNSSEC validates those, and if it doesn't validate, they won't give you a cert. Komodo, on the other hand, is still of yep, the credit card works, and that's their validation. So they got certs from Komodo for the PCH networks. And so what they would do was, at that hour, they would change the DNSs, and they would now point to their own, which had IMAP and web and other things pointing to machines of theirs that they had set up, man-in-the-middled. And PCH, because they were doing DNSSEC, and they hadn't disabled DNSSEC, it didn't validate. And what they discovered was that their IMAP client, when you can't reach the site or when it fails to log in, it simply says no new mail. It doesn't give you an error, I can't get to the other site. So it was during the Christmas holidays anyway, traffic was lighter, and it only happened for an hour, and so they were going, oh, I'm just getting less mail than usual. Okay. The problem was 2 of their employees were at a hotel with a captive portal that required using their DNS recursive resolver. It was not doing DNSSEC validation. Fun number 1. Fun number 2, they were on iPhones, which as soon as they locked and got an IP address, even before they had validated with the open portal, were immediately trying to log in, and they were getting the non-DNSSEC validated incorrect IMAP. So they were connecting to the false site. So these guys got the 2 employees' passwords. And once they had the passwords, they already could get into the registries and make changes there, which they were. Now they could get it to emails. So they went into emails. They also started hopping around to see if they could SSH in, finding what other machines these 2 employees had access to, and then just copying every file they found and every password file they found and dumping them off for later use. And so they just did this 4 times over a couple of weeks. And among other things, they managed to get passwords for customers of these registries, which included the .uae or gov.uae and gov.whatever Lebanon's 2-letter country code is. And once they had those, they could make changes in the DNS zone files for those. And they would flip those for an hour, and they started getting government employee credentials and email. And that was basically their entire goal. They wanted to be able to walk around silently and unnoticed through their enemy country's government official sites, email, and whatever to do espionage. And if they hadn't had some of these things breaking because of DNSSEC popping in and out, it probably would have gone a lot longer before it was noticed. So basically at that point, 2 sovereign nations were owned by one of their enemies who had access to all of their sensitive information. Now, there's a lot of stuff that were learned, and actually Bill Woodcock did a presentation on this a few weeks ago of all the things that happened and all the things they learned. It's the ICANN DNS Symposium, and I'm pretty sure there's a link in the further reading. Check it out, because he did a very open and forthright breakdown of root causes and lessons learned. One of them was part of the problem with doing things was they were checking NS records in the parent and DS records, but because they had such long TTLs, they were checking it every 24 hours. And these guys were coming in for an hour at a time and going away. So they didn't catch that. They also realized that when they did a directed graph of all the links in the chain of all of the DNS delegations and who owned them and who could do password recoveries and get account credentials, or who could change them and how many people knew it and all the rest of it, and they did essentially a risk assessment, they realized that they actually needed to check NS and DS for changes for everything from the root all the way down to exactly the labels that they cared about, and on a much more aggressive basis. So they are now doing that, and they're walking the full tree, validating the full tree, and doing it on, I think, like a 3 or 5 minute interval. There's also something that you can have in both the registrar account that you as a consumer have, and that you can ask the registry to do, locking, which is exactly like doing a credit lock on your credit cards, where you lock it and you have to actually call somebody up and give some password or some much more extensive than you could log in to open it up so that you can make changes in or have access to your credit history. And you can do the same thing with your registrar account and registry. Yes, it means that you might have to have somebody woken up and get out of bed if there's some emergency and you need to change the NS records. But the odds are pretty good that most of the time you're going to be doing that and it's planned, and you're going to have a checklist, and you're going to be giving change management procedures out, and you're going to be notifying your customers. And so it really shouldn't slow it down, but it really puts a dead stop to somebody malicious trying to do that, particularly if they're trying to pop it every hour. So that was there. At the time, not everything they had multi-factor authentication enabled. It was available, but it was not on everything they had. They also, it hadn't really occurred to them that having their IMAP server, something that you could IMAP into directly from the internet, from the open, not over a VPN or an SSL tunnel, was one of the other reasons why it mattered that their 2 employees were there, because if they had been over an encrypted tunnel, even going through a hostile network, that wouldn't have leaked their credentials. And so they actually re-architected all of their service machines so that nothing did anything more than one thing. It was all behind firewalls. You had to use VPN access. You had to use VPN access that had 2-factor. All of those were things they learned. They also discovered that it was very easy to change the resolvers on the phone, the stub resolvers. And they turned on the MDM stuff where, basically your IT department owns your phone. I both hate and love this. It's very secure and it's annoying beyond words because IT staff. But in this case, that was another. They have too many people who are in hotels all over the world because they're global, and they are going into places like China and other places where that the government is one of the actors that is trying to get into your data. DNSSEC would have helped, and it did, except for the fact that they were forced to use a resolver that didn't work. One of the things that Woody and I both think there should be more of, I've said multiple times now, the CA insert stuff sucks. It's horrible. Everyone should be telling every browser vendor, every time you talk to them, Dane isn't enough slower that you shouldn't do it. Dane is a much better, cleaner, and more logical leap of trust for doing certificates for web. So, what can you do? Everything you should be doing everywhere else every time the term InfoSec pops up. So, decent passwords. Don't reuse passwords. Preferably use a password manager. You can even have group vaults that you can give and revoke access to employees as they come in and out. Use multi-factor. Almost everything these days supports it. Phishing training. If some of their staff had noticed earlier that email was doing wonky things, that might have been another chance for them to catch it during one of the first couple of attempts as opposed to after attempt number 4. Actually not attempt, after success number 4. Other things that you start looking at when you start getting paranoid. That registrar account that you have, or the registry account, in many cases somebody registers their domain name and they're your web designer because it's for a campaign. And they use their own email as the contact for it, and that becomes your password recovery account. And it might not be someone at your company, or it might be somebody you left. So make sure that every domain you care about, that the contact emails are either role or a current company employee, so that nobody else can change your password and get into your account. And go through all of that regularly. Go through that directed graph of where are all my dependencies, where are all the places they could change permissions or steal credentials and come at me from behind or the side. Monitor your DNS, and not just yours, the whole chain, the parent, all of it, and do it on a very regular basis. 5 minutes at a time, 10 minutes at a time. Do it from multiple different places. Use one of the RIPE Atlas, Thousand Eyes, something that is across lots and lots of ASs so that you get an idea of what it looks like everywhere on the internet, not just from the path from your data center. And anything you care about, you should be monitoring those records. And in all cases, monitoring is useless if you don't page somebody. So actual have alerts for things that you care about or that are unexpected. SSL certs and certificate transparencies, at least attempt it. And there are debates about whether the more extensive certs are actually worth the money that they charge for them. But if it's millions of dollars of income to you that might go away if your website is out, it's worth getting a better than the credit card cleared version of the cert. And Dane. And ACLs, VPNs, tunnels. Again, it's all just the standard stuff. And then validate on your recursive. If you're going to sign things, you should be validating so that you know that DNSSEC is broken. And sign everything. And registry lock everything. And registrar lock everything. All right, so we've got a little, how much time? About 15, 20 minutes? So I sort of blew through this, but I'd love to have questions on either other incidents or more details on these.
Hello, I'm Sergey. Just a small addition to a previous slide. Can you slide back? Maybe one more. Yeah. Talk to you, insurance company.
These guys know risk versus money better than anybody. That's their whole business. Yeah, it's a good suggestion. Thank you.
Damian Mencher from Google. One thing I didn't hear you mention is HSTS headers. So just a quick comment, or do you want to describe it?
You'll do better than I will with it. I sort of know, but yeah.
So web browsers have this option for host strict transport security. So basically, a website can respond to its customer saying, in all future transactions, you must use SSL, and the certificate must match. The user isn't allowed to click through that. So as an example, if like my Ether wallet had done this, their users would not have been able to click through these warnings, and they would have been better protected.
Yeah, and my understanding is it's basically much like the SSH fingerprint the first time you go in, and then after that, if you don't present one of the acceptable ones, you actually get an error. Or you don't.
I don't think there's actually a certificate. So when you buy a fraudulent certificate from Komodo, you do bypass this. It's not certificate pinning. It's just it requires a valid cert. So it's not bulletproof. But
yeah, the whole cert system in general is fraught with peril, but yes.
I also had a question. I vaguely recall hearing that one of the things, as you know, I'm interested in DNS amplification attacks.
Yes.
All of these attacks come from DNSSEC signed domains because they have very large any records, right? So this is why they're almost always government domains, because the government is all happy about DNSSEC. I vaguely recall hearing talk about trying to shrink these records so that they aren't quite as large.
Yes, so there are a couple of one of them is current best practices to not allow any, or to rate limit it, or to ACL it so that only your NOC can ask for any. So that's one of the pieces. And there are also other things with rate limits so that you can't get quite as many. The other probably big win is algorithm choice. ECDSA has the same cryptographic strength as RSA SHA-1 for a fraction of the size. I will point out, of course, also that I have seen people doing spectacularly stupid things like putting 40A records in and then having your app doing magic load balancing instead of doing it in a more sane way. And that's going to be huge, and people have text records. But yes, anything you can do to deliberately keep your response sizes. And also with V6 these days, if you can keep it below 1280, life is much better. Packet fragmentation and DNS are not friends. Thank you. Other questions? Okay, so like I said, somewhere, pull down the slide deck. I've got some stuff with more detail, and definitely do check those out. Oh no. Yeah, so those are worth reading. There are a couple of them, like the ICANN doc, that also actually themselves refer to other things. The government gave out recommendations for using DNSSEC and doing other security stuff and doing two-factor. So there's plenty of good advice out there, but how long has BCP 38 been out? So yeah, if you can turn this stuff on at where you are, at least we're getting ahead. All right, if there are any other questions, thank you very much for your time.